Tony.
Thank you very much, Suzanne. It's great to be here. So, as you said in your introduction, I symbolize, if you like, Microsoft's renewed interest in supporting the scientific and technical community. Traditionally, we've focused on enterprise and consumer, but now we really wish to see how we can bring benefits to technical computing community. So, what I'd like to do is give a rather high-level overview of the field at this moment and pick out some trends that I think are important. So I'm going to start with what looks rather like an academic trend, but actually I believe is not. I believe it underpins a lot of the industrial applications we will see in the future. So I think we're seeing the emergence of a new science paradigm. I mean, thousands of years ago we devised experimental science where we observe and record the aspects of nature around us. And then with Newton and Galileo and so on a few hundred years ago, we saw the beginnings of theoretical science based on equations, force equals mass times acceleration, Maxwell's equations, the Schrödinger equation, and so on. And so those have been traditionally the two bastions of science and engineering for the last few hundred years. But in the last few decades, I think it's fair to say that computational science and engineering has come of age. That now it's everybody from academia to industry, except that computation is absolutely an essential part of the armory of attacking the problems of today. And traditionally, things like simulating climate modeling over periods of hundreds of years or thousands of years cannot be done any other way. Colliding galaxies in astronomy can't be done any other way. And in industrial simulations, car crash simulation, whole plane simulation is also now a standard tool for the industry. But I think in the next 5 or 10 years, you will see the emergence of a slightly different focus to this, of which high-performance computing will be part. But if you like, it's what I call e-science or data-centric science. So it's the emergence of new instruments and technologies for producing vast amounts of data, high-throughput devices, satellite surveys, data captured by simulations, sensor networks, and so on, will generate, much more data than we've ever collected in the whole of human history. And this will be available for analysis and for mining. And to do that, one will need different types of tools. One will need intelligent data mining. One will need clusters where the data is, rather than trying to move petabytes of data. So I think that's going to be an important trend. So if I were to summarize e-science, it's about data-driven science, which is bigger than you can hold on your workstation, so it's distributed around the world, maybe in different data centers and so on, and you have to bring them together to integrate, federate, and analyze this type of data. And typically, it's the belief of most economies nowadays that it's the interfaces of fields like bioinformatics, chemoinformatics, whole systems biology, and so on. These interfaces are where big high-value developments are going to be made. So these are typically distributed, so because areas such as the pharmaceutical industry, it's no use for the chemist to sit in their laboratory not talking to the physicists, not talking to the biologists and the genomicists. They have to collaborate, and that's often within an organization, but increasingly it will be between different organizations. So we will need to have these distributed ways of collecting, sharing resources in a secure manner. And so this will all be driven by huge amounts of data in almost every field. In something like the bio area, there's genome data, there's two-dimensional microarray data, there's protein structures and so on. Different types of data. We want to go from data to information to knowledge. And e-science, if you like, is a shorthand for the set of technologies to support that. In the US, that's more or less synonymous with the US initiative that NSF are now launching, the Cyber Infrastructure Initiative. And what was interesting to me in the UK e-science program that I ran for the last 5 years, was that it wasn't just the scientific community. We had over 80 companies engaged in this, and Simon, in his talk later on, will talk about some of the examples from that. So we see that high-performance computing is a key technology to support this e-science revolution in all its aspects. Before I go on, I should actually just give some definitions of what I mean by a cluster. So a cluster is a set of computers which are viewed as a unified system within one administrative domain. Typically, it will be built from commodity components, commodity processors, commodity interconnect. We also see on the horizon grids, which, if you like, are virtual organizations. Could be within one company firewall, but it could be between companies, it could be between universities, between laboratories. And these are configured from sets of resources, not only compute resources, but also data and instruments, which are in different administrative domains. And so we see this as an important trend. So this is a graph from Jack Dongara's top 500, and it shows the evolution of the top 500 machines in terms of the Linpack benchmark over the last 15 years or so. And on the left-hand side, you can see, just looking at the colors, that there are many different colors, and you see architectures like SIMD and Vector. But what I just want to point out on the right-hand side is the preponderance of the yellow in the middle, which is the emergence of clusters as a commodity. And so these are clusters built out of commodity processors using largely commodity interconnect, and these are beginning to dominate the high end. And these are now, rather than exotic beasts, these are now built of affordable components and are changing the face of supercomputing. So in Microsoft, although we have a representative target, we can actually perform in the top 500, I think it's fair to say that our dominant focus would not be in the top 500 systems, but if you like, in the bottom 250,000. We believe that there's going to be an explosion of growth there, and actually that's where we think the high-performance computing market is going to transform the way engineering and science is done. The major drivers are fairly obvious. Market pressures are demanding accelerated innovation cycle, shorter time to market, and so on. And modeling is becoming an increasingly important component, because you can replace time for wind tunnel testing and so on. You can actually do more modeling and design more of the system without resorting to physical models, and that reduces your costs and increases reduces also the time to market. So again, this is going to be driven by the cost reduction, because this is built out of commodity hardware components. We're going to see high performance systems everywhere, and in addition, because the ISVs are understanding the importance of this market, the key major engineering and bio codes and so on, oil and gas codes, will already be parallelized. So you can almost now go and buy a box, put under your desk, and you've been running on a single processor. You know, you press a button and you get the performance from your multiprocessor, already parallelized code. And that's going to transform the way small businesses, researchers do their way, because now they can get this high performance computing in a personal capacity for the individual scientist or engineer. And we think that's to be a major growth area in the near future. And so this just illustrates dramatically the cost reductions. 1991, Clay YMP, a 10 gigaflop system, the list price, whatever that means, was around $40 million. 98, as a Sun example here, 10 gigaflop system cost you around $1 million. But in 2005, just looking at components that you can put together, x86 processors, gigabit Ethernet, 10 gigaflop system, you can put together for a few $1,000s. So really dramatic changes in cost. And what we see is a continuing trend here. So we're now going to see personal clusters and workstations giving you unrivaled performance that you've never had before at your desktop. But if you want larger systems, you can go down the hallway and connect to other clusters and connect to national supercomputers and so on. So we'll see grids, connections of these resources becoming ubiquitous in the next 5 to 10 years. And again, the IT industry has united on a way of building more robust distributed systems, which is based on a service-oriented approach. Instead of building distributed systems where you actually address individual resources behind someone's firewall, now you expose what service you're going to supply as a service definition, and you expose that. How you deliver that service is up to the company. So if you're addressing that, no longer are you addressing a specific resource, you're addressing a service, and how that's supplied on which machine and so on, whether you make changes behind your firewall, doesn't affect the other user. So the IT industry is united that this sort of service orientation, web services approach will help build more robust distributed systems. So the other major trend, I see that we will see the emergence, and I don't think we're mature yet, but we will see grid systems becoming available, offering HPC services, data services, workflow, underpinning all the application services. And so these will be built on basic web services, and they will allow users to build the virtual organizations necessary for them to do their job. And underpinning this, we will see now that the web services security stack is now, the specifications are now out for debate. We will see WS policy, WS trust, and so on, putting together a really robust and easy to deploy security solution which gives real comfort to organizations sharing data, that they can share data in a controlled way and manage access. And I think the other major driver could be the merger of the Global Grid Forum with the Enterprise Grid Alliance, which is sort of a more researchy organization with an enterprise organization, and this can combine the best of both worlds. I think it will benefit the entire industry and grow the market if we can agree some simple grid service standards on top of these now pretty mature web services that will grow the market for everybody, and that should be driven by the market industry. But the academic research community, they have a vital role in exploring new types of services, seeing which are mature, which work, which don't, and they're important for our future. So looking a bit further out, 5 to 10 years, this is a slide from Pat Gelsinger of Intel showing the power density on a chip. And up to now, with Moore's law for the last 30 years, they've shrunk the size of the transistors, and at the same time you could reduce the voltage and increase the cycle speed. So along with more transistors per unit area, you also got a performance improvement, if you like, for free. But now, because you see that the temperatures and the power density if you continue this projection, become unsustainable, chips melt and so on, that actually we're not going to see that increase continuing. We're going to see that the processor won't get faster, but what you will see that the transistors will continue to shrink. And the challenge for the IT industry is therefore how we would deal with the fact that we will have processors which don't go faster individually, but you will have hundreds of processors on a chip, as Justin Ratner says, by 2015. That's less than 10 years away. So how will you make use of that? Already we're seeing dual core, quad core, and eight cores will be common in the near future. How will we use that? How will we make programming applications easy? I spent 20 years in an academic doing parallel computing, and all we came up with was message passing. Can we make it a really easier paradigm for developing consumer applications and real applications for the IT industry? And there is a challenge for the technical computing community. How will it use multi-cores in its scientific and technical applications? That's going to be a challenge because it's yet another memory hierarchy. How will we deal with that? So I think it's an exciting future. I think it's going to be transformed by these commodity clusters, but I think there are challenges in the future from these multi-core chips. Thank you, Suzanne.
Thanks, Tony. And let me just remind our audience that you can submit questions for our live Q&A session, which will come at the end by using the Ask a Question box. And we now have the audience's response to our first polling question, which was, how would you best describe your role within your organization? 15.2% of you said IT architect. Another 8.6% said software developer. 32.6% said scientist user. 15.2% IT manager, and finally 28.2% responded other. So our largest response was scientist user at 32.6%. So would anyone on our panel like to comment on the results?
Well, yes, can I say I'm very gratified that there are the users out there. It's clearly the IT architect needs to understand how clusters fit into the overall architect for the company or for the organization, and it's clearly going to be a heterogeneous world with multiple systems out there. And software developers have a challenge in how to develop software for this, but it's the scientist user, I think, are going to drive this, and really, if we can get them engaged and understanding that this can actually transform the way they do their business, their day-to-day business, then I think that's a really encouraging sign. And the IT manager needs to be aware of the impact of clusters and grids on the business. And so it's a gratifying spread that you have in the audience.